Hello everyone, welcome to lecture 4 of this course series on electrostatic, more specifically electrostatic conductors. I am Dhiraj Madan, and in today's lecture we will be looking at the idea of electrostatic shielding. So in the last lecture we had discussed a few problems based on different configuration of charges within cavities. We looked at the case wherein we can have multiple possible shells, each of which lie within another. Right. And we also saw that we learned how to compute the charges on each of the surfaces, right? However, if you want to use that same idea to compute the electric field or potential within the regions within or outside the cavity, then essentially the idea is that sometimes those ideas are not sufficient. More specifically, if your cavity, for example, is irregularly shaped, then how do you compute that? So in many cases, these sort of problems can be solved like quite easily using the idea of electrostatic shielding. I hinted at this in one of the problems in the last lecture as well, if you remember. So for example, uh, so basically, if you have like a plane cavity, right? If you have an electrostatic cavity, and let's say the total charge on this conducting medium is capital Q, and let's say there are some external charges also. So we saw that within the cavity, the net charge on the inner surface is always zero. And moreover, there is no field inside the cavity, because if there is field, there are going to be field lines, and that will create a potential difference, which is not possible, right? So essentially this, we saw that, this cavity shields us from all the external charges. So essentially this is at a high level the idea behind electrostatic shielding, which we will look at in today's lecture in more detail, right? Before that, I would also want you to, just revise the 5 properties we have seen for electrostatic conductors. So firstly, the electric field within the conducting medium is always zero. Secondly, there is no charge which can lie within the conducting medium. Thirdly, any charge which is there on the conductor must lie on the surface of the conducting medium, because it cannot lie within the mass or within the medium. Fourthly, all points on the conductor are at equal potential. And finally, the electric field outside the surface must be perpendicular to the surface. So these were the 5 properties which we have looked at in the first lecture of the series. And we have been using this property again and again in different lectures, right? With different ideas and different sort of problems we have been looking at. Uh, Now let's come back to the idea of electrostatic shielding, right? So let's look at one of the problems which we also looked at in the last lecture again. So essentially, let's say you have a conducting medium with a cavity, okay? And let us say within the cavity I place a charge of capital Q. Okay. Uh, okay. And let's say I want to compute the electric field outside this cavity. How do we do that? So we have seen how to compute the charges on the inner and outer surfaces, right? So how do you compute the charge on the inner surface? Well, what you can do is that you can consider a Gaussian surface which passes through the conducting medium. So say this is a sort of a Gaussian surface which passes within the conducting medium, right? And we know that within the conducting medium, the electric field is going to be zero. So applying Gauss's law, we see that integral of E dot dA must be zero, which means that the total charge enclosed must also be zero. So the total charge enclosed includes this point charge, which is capital Q, and the charge induced on the surface, which I'm going to call Q inner. Right? And then, the remaining charge, Q outer, is going to lie on the outer surface. The total charge on this sort of conducting medium in this particular example is zero. So here essentially apply Gauss's law. So let me just actually, I should have written down the problem statement. Let me do that now. So consider a conducting medium having a charge of Q, okay, within a cavity inside and zero charge on the medium. Actually, I should have called it a conducting shell. Okay, so compute the electric field outside the uh, outside the shell. So essentially, the idea, what we are given is that the outer surface is spherical with radius r, and inner is irregularly shaped. Okay, so this is what we are given to us. Now the idea is that we apply Gauss law, wherein the Gaussian surface passes through the medium, so this orange dotted surface, to get that the charge enclosed on the inner surface must be zero. This implies that the charge on the outer surface must be minus q, right? Because total charge is zero. So if minus q is on the inner surface, then the remaining on the outer surface must be so basically, okay, so minus q is on the inner surface, which means that on the outer surface we must have plus q, right? So why is minus q there on the inner surface? Because total charge enclosed within this Gaussian surface is q inner plus capital Q, which implies that q inner plus capital Q must be zero, or q inner must be minus of capital Q. The remaining charge which is left on the outer surface is now plus of capital Q. Uh, okay, so this is the configuration of charges we have computed. Now the problem asks us to compute the electric field outside the shell. So how do we do that? So the idea is that, okay, so here's a total, here's a point charge of plus q, which is inside. There is minus q induced on the inner surface, and then finally a plus q which is induced on the outer surface. Now the electric field outside the sphere so it can have the following sort of sources, right? So it can be due to, so what are the sources? So first is the point charge plus q inside. So if I have to compute, somewhere outside, right, let's say over here, if I have to compute the electric field, so it could be influenced by this point charge, it could be influenced by the charge induced on the inner surface, it could be influenced by the charge induced on the outside surface. So it can be due to point charge plus q, next charge on the inner surface minus q, and then thirdly the leftover charge on outer surface, which is plus q, right? So there are these three sources of electric fields. How do we now compute the net effect? So we can compute the effect of the point charge plus q. Well, that's easy. We can directly apply Coulomb's law. But what about the charge induced on the inner surface? So the idea is that this inner surface is now an irregular surface, and it is very difficult to quantify the distribution which is happening, which is there on the inner surface. In fact, I haven't even specified the shape of the inner surface in the problem. Okay. And thirdly, on the outer surface, I know that, okay, well, at least the surface is spherical, it's spherically shaped, but I do not know whether, whether the distribution on the surface is uniform or not, right? So I just know that there is a leftover charge of plus q. So what's the distribution? I do not know. And without that, it might be difficult to compute the electric field. So what happens over here is that, okay, and I'll just directly tell you the answer, and the reason we will come to now is the idea of electrostatic shielding. So we can show that. So firstly, so the fields due to point charge plus q and the inner surface, and the one which is induced on the inner surface, which is minus q, they cancel at all points, okay, within conducting medium. Within conducting medium, they have to cancel. Why? Because we know, due to the idea of, so within the conducting medium, they have to cancel because inside the conducting medium, the net electric field has to be zero within the conducting medium and outside the shell. Basically, outside this space, that over that entire space, they will definitely, or both of them will cancel. And the charge on outer surface is uniformly distributed. So now the question is why? Okay, why is it so? That's what we will be discussing. So assuming that this is true, you can very easily calculate, right? Because to compute the electric field outside this, you can just take these two, they cancel away. This is plus q, you compute the electric field due to the charge plus q, that is q over 4 pi epsilon naught r square r. That's very simple, right? You can easily do that. But now the question is that, why do they actually just cancel away? And why is it uniform? So that's the question. And to understand that, we'll have to look at the idea of shielding of conductors. So basically, the idea in case of shielding effect is as follows: that if you have a region which is bounded by some sort of conducting surfaces, then in order to compute the electric field within the region, you need to know the charge density within that region. That is as follows. But on each of these conducting surfaces, you only need to know the total charge on the conducting surfaces, right? The distribution uh, will actually be determined on its own. So that's what we will be looking at. And then we'll apply that to sources. Right? So basically, whatever is happening within that conducting surface, that you can just throw away. That's what we look at. Let me give you this theorem. This is called as uniqueness theorem. What it says is as follows: that if a region is bounded by conducting surface, then the electric field is Uniquely determined by one. Firstly, the charges or charge density within the region. And secondly, the total charge on each surface. Okay. So basically, that's what this particular theorem says, that if you know there is some region and it is bounded by conducting surface, then you need to know the charge density within each region to compute the electric field within the region, and the surfaces which are bounding that region. So let's take the previous example only and let's try to understand this. So in the previous example, what we had was this spherical surface, right? And there was a cavity inside this. So what I do is that I split this into two regions. So first is the, let's say the region within the cavity R1, and then there is a region outside the cavity which is R2. Okay. Now the question is to compute the electric field outside this conducting medium in this area in R2. So if you see that there is no charge first of all inside this region R2, and the idea is that if I want to compute the the electric field within the region R2, what I need to know is that I need to know the okay, so this region R2 is bounded by this sort of conducting surface. So R2 is bounded by outer surface. So to compute the sort of electric field in the region R2, what I need to do is that I need to know the charge densities within R2, and what I need to know is that I need to know the total charge on this bounding surface R2. Bounding surface for R2, right? So basically here the charge is Q. On this inner surface the charge is minus Q. On this outer surface the charge is plus Q. So what this particular uniqueness theorem says is that I need to know the charge density within the region, okay, and the total charge on each surface which bounds the region. So if we look at this R2, and for this R2, if I want to compute, so basically the net, there are no charges in R2, and this particular surface has a net charge of Q, and whatever is inside this, right, for the purposes of computing electric field inside R2, what I can do is that I can just plainly ignore this. Right? So whatever is inside, it doesn't matter. What matters to me is the charge on the surface which bounds R2. If I want to compute the sort of electric field within R2, then essentially I don't have to look at what is inside the surface. I just need to know the total charge on the surface. So if the total charge on the surface is Q, and let's say I just replace everything inside it by I just fill it up with a conducting medium entirely, then also for R2 it should not matter how much is the electric field. So if I just fill it up with conducting material, then essentially the this capital Q is uniformly distributed. At any point the net electric field is going to be Q over 4 pi epsilon naught R square R cap, right? So whether the point charge is placed at the center of this shell, whether it's placed somewhere else, whatever is the shape of the cavity, it doesn't matter to me. What matters to me is the net charge on the outer surface. How did I compute the charge on the outer surface? Well, I know the point charge is Q. I apply Gauss law. I come to know that the charge on the inner surface is minus Q. From there, I compute that the charge on the outer surface must be plus Q. Right. After that, I can just throw away whatever is inside this conducting in this cavity. I just replace it uniformly with the conducting medium. This is already a uniform spherical shell. Essentially, charges are uniformly distributed, and at any point, the electric field outside is given by Q over 4 pi epsilon naught R square R cap for R greater than equal to R. That's what I have computed. Inside the cavity, well, this problem doesn't ask us to compute the electric field inside, but that will be slightly difficult because we don't know the distribution. Right? In fact, without knowing the shape, we cannot. But outside, we can easily compute. Inside the medium also, I know that the electric fields are zero. Inside the cavity, I can. So let's look at another problem. By the way, we can also compute potential also. So that I'm leaving as a homework exercise. So compute the potential at points outside the outer shell, outer surface. This is also homework exercise. So let's look at another problem. So now what we have is that we have another cavity wherein the inner surface of the cavity is spherical and outer surface is it's some irregular shaped. And there is a point charge plus q at the center, right? And you need to compute the electric field at points within the cavity. So again, as before, you can compute that the charge induced on the inner surface is minus q, on the outer surface is plus q. And now the thing is that we again apply that same uniqueness theorem. Right? So if you, so basically the idea is that if we look at this region inside, right? So let's look at this particular region R1 now. So in this region R1, if I want to compute the electric field, I need to know how much is the sort of so I need to know how much is the uh, mm, what is the distribution of charges inside this, and I need to know the total charges on the surface which bounds R1, right? So basically this particular surface, this uniform spherical surface now bounds R1, right? And whatever is outside, that's immaterial to me. So whatever is outside, it doesn't even matter to me. I just sort of ignore. If I want to compute the sort of electric field inside this, I only need to look at the charges inside and the net charge on the surface. So the net charge on the surface now is minus q, and we have plus q at the center. And now you can just apply Gauss's law. There is a sort of symmetry. You can compute that electric field within the region for r less than r strictly less than r is just q over 4 pi epsilon naught r square r cap. So that's very easy for you to compute. So in general, the idea is that the general idea. So this is within the cavity, within R. Right? Outside it, you just throw it away, just note the total charge on the surface. The general idea is that you can use Gauss's law to compute electric field on each surface. Secondly, use uniqueness theorem to divide the regions separated by conductors and compute electric field in each region separately. that's it for today's lecture. So let me just revise what we did today. So the idea was that, we started with a problem wherein there was a cavity wherein a charge was placed inside. We wanted to know the inner surface of the cavity was asymmetrical, whereas outer surface was a perfect sphere. We wanted to compute the electric field outside the outer spherical surface. The idea is that we split this into two regions. One is region within the cavity and the other is region outside the cavity. We want to compute the electric field in the region outside the shell. So the idea is that in order to do that, what we can do is that we can just ignore everything which is within the shell. Okay, so whatever is within the conducting surface, we can ignore, and we only need to compute the total charge. So total charge we first compute using Gauss law. So point charge Q is inside, minus Q is induced on the inner surface, plus Q is induced on the outer surface. Once we know that, to compute the charge outside the sort of this sphere, then essentially what we do is that we just ignore whatever is inside the surface. We just note the total charge, which is plus Q on the surface. And if we need to see if there is any other charge in the outer region, there is none. So we can just use the usual way. We can apply Gauss's law. We can compute the electric field outside this region as Q over 4 pi epsilon naught R square R cap. We looked at another problem wherein the charge plus Q was again inside, but now essentially the outer surface of this was irregular. So what we do is that in order to compute the electric field inside, we can ignore everything outside the inner surface. Inner surface, the net charge is minus Q. That's what we want. So once we do that, once we take the inner charge of minus Q, point charge plus Q inside, we want to compute the electric field inside R1. We can just apply Gauss's law. We'll again get Q over 4 pi epsilon naught R square R cap. So note that what this theorem says is that, if there is a region you can find which is bounded by conducting surfaces, then essentially what you need to know is that you need to know the charge density within the region, and you need to know the total charge on each of those surfaces. Rest everything which is which is sort of enclosed by the surface, you can ignore. And this idea of ignoring it is the shielding effect, that if whenever you have a conducting medium, it will shield the inner part from the outer part and outer part from the inner part. So that's what we have over here. Okay, so do look at this video again and try to grasp this. So that's quite an important concept. So hope you liked it. Thanks. Bye.